All right. Welcome back, everyone. Along our journey here, we see that we get in a lot of 4 vectors and we have to deal with them. Our next one is, of course, the invariant product of the 4 velocity with itself. Okay, so that is eta mu times eta mu. Of course, look at this notation. We have a contravariant and a covariant 4 vector, and so we're going to have to be careful with that. We want to know, is eta mu time-like, space-like, or light-like? Okay, so we really want to know what is the invariant product or the invariant interval leading. Is it positive, negative, or 0? That being said, the proper velocity for a vector is defined as eta is equal to 1 over the square root of 1 minus u squared c squared times the ordinary velocity u, with the 0 component equaling c over the square root of 1 minus u over c squared. Again, similar formats here, except now we have c for the temporal domain. Let's also recall that writing out this vector product, or the 4 vector, in the contravariant form, is 0, 1, 2, 3, 4. Again, the 0 is the temporal. Then we have x, y, and z for our normal 4 vectors. And so that's why we normally write out eta 0, and then this is just the normal velocity vector that we would have. But let's see how to deal with this. All right, so the 4 vector listed is in contravariant form, i.e. the index is to the upper. And what we also need is the covariant form, where its index is to the lower. What we need to know is that in order to shift it to calculate the invariant interval, as far as the dot product is concerned, we need the indices to match. So to transform this, all we need to do is change the sign on the 0th component. So all lower indices get raised to upper if we change the sign on the 0th component. Again, that's just to make sure everything works out. That's a handy trick. And again, be very careful. So what we say is that upper indices designate contravariant and lower indices designate covariant. Again, definition is going to get spewed, but at least you know, change the sign on the 0th component before you try to calculate the dot product. That being said, we see we get eta 0, eta dot eta 0, eta, and that gives us the negative here. Then we just have eta 0 squared plus the normal eta squared, which is the dot product. Therefore, we could plug in both of these components that we saw earlier, the c over the square root plus the 1 and the u over the square root, where the u will just be a dot product with itself. So we get c squared plus u squared over this nasty looking fraction. So we can add, thanks to being a common denominator, and we see that we could factor a negative c squared out, and we get a 1 here, but we also have to force factor this c squared out, so we have to put it under the u squared. But we notice when we do that, we just cancel away the factors, and that leaves us with a negative c squared, which when we compare to the chart that we were given, tells us that we are time-like. Okay, so that's pretty cool to see, and there's a lot more to be said about those things and how they add up to something that we can understand as far as what 2 events are. But it's nice to see that the invariant interval just gives us the negative c squared, and that's going to be the same before and after, and hence the invariancy of it. That being said, we will use this result at some point later, so we'll check you then.